Um, Hello everyone. I'm Jasmine Calma, the Women Tech Maker for GDG Cloud, a Women Tech Maker ambassador for GDG Cloud Manila. Yes, yeah. Um, for our first Women in Tech webinar, our speaker is a Google Cloud developer expert in machine learning and a professional Google Cloud architect. Today, she will talk about how to build privacy-enabled distributed systems using GCP and TensorFlow encryption packages. To not keep you waiting, I present to you Sharmistha Chatterjee.
Let me share my screen. Are you able to see my screen? Jasmine? Hope you're able to see my screen.
Yep, I can see your
Yeah.
screen.
Yeah. Okay. So I'm just not a much introduction. Jasmine has already told about that I'm a GD expert in machine learning, and I currently work at Publicis Sapient. The slide is already uploaded in SlideShare, so you can look at it. Have a look at my website, takeairesearch.com. I have all put the blogs which I try to do on differential privacy or any other thing. It's already available in GitHub code. And the Hacker Noon also, I shared the link where the differential privacy blog I have written. So what are the key takeaways today? What we are going to learn? Let's have a look at it. So why privacy in machine learning is important? What are the privacy attacks and laws, and how we can be very careful that we don't violate these attacks? So what things we should introduce in our machine learning models so that we are safe against these attacks? And we have to do that because there are laws asking us to do this in different countries or continents. Laws have come and they are very strict. So companies will end up paying billions of dollars if we violate the laws. Then they will look at the life cycle in data science. What is the life cycle of privacy preserving machine learning? What are the techniques when you take a raw data and you put it into the cloud? How it goes? Which phases do we add privacy? How do we add? Then we look at TensorFlow package TF encrypted. There is another package which is wrapping TensorFlow encrypted. I'll show you that. I have shared already that package name. Just download from GitHub and you can try it out. With federated learning in terms of lot of devices are there. How does this package help us to encrypt the machine ML models, the data, and how does it help to train the models? Then we will talk about differential privacy. Differential privacy at the application level. How do we build those differential private? How do we measure what is differential privacy? What do we measure? And how do we achieve what is accuracy? What is privacy preserving ML model? How do we measure those terms? Let's have a look at it. And then ultimately, I'll go into how do we productionize those solutions. Here, some of the GCP packages I will talk about that you can use to build an end-to-end solution and that you can deploy in any cloud. Like for GCP, I'll show you what are the packages you can use. And then once you deploy, how do you monitor? And it is a life cycle. You remember that we have talked about it is a life cycle. So it is an ongoing monitoring system and how you can improve your solution. So let's get started. So are companies data safe? It's not at all. You can see that Facebook, whether it is social media or it is travel and hospitality, Uber, British Airways, or Equifax, they have ended paying billions of dollars as fines because they have violated security acts. Their systems have been compromised and users' data and user-sensitive information have got leaked. And so you can see the volume of data that has leaked and has caused them to pay even billions, not even millions and billions of dollars of fine. So we have to be not only from the perspective of big data, but also from the perspective of machine learning, we need to be very safe. Here also you see how the attacks happen. Suppose even if you have not given your sensitive information in one system, but you have the details are available in somewhere else, like the NYC taxi limousine attack. What happened is this is called linking attack. So in one place, some details in some part of my very private information is available, like the celebrity information where they are traveling, it's available. But in some other system, there is the more details of the celebrity, like what is their age, what is the sex, what is their preference, etc. details are available. So what the attackers will do, they will try to link between the sensitive information, some private information, credit card or something like their income, some their bank details. They will try to link some information from this to the main system, like where their more generic information is present. Even in the first system where the sensitive information doesn't have their details, they will try to co-link these two things, and ultimately they will be able to get retrieve all the information. We have seen such kind of attacks with AOL search logs, where the logs are there and it didn't have, it had some information but it didn't have very the secret information, but in some other place in the log that has secret, they can combine that and they can get all the details, who is having what, who is credit card is what, everything, all sensitive information. Same we can see with even with the Strata's witness tracker heat map, and Netflix and IMDb data. Attackers were able to combine those and get retrieve all those data. And so group insurance company also found their system has been compromised with this kind of linking attacks. And there are also other syntactic attacks like Trojan horns, which are attacking the models and they are trying to get the information. Now let's see in machine learning model how these attacks are happening. So there is raw data coming into the machine learning, the feature vectors get extracted and the models get trained. Now we have two types of attacks. One is the model inversion attacks, and what is that is a kind of black box attack. So the attacker doesn't have any information to the machine learning model, but he tries to extract this information and he preserves that in terms of in terms of feature vectors. And then after he has done the black box attacks, he will do reconstruction attacks to get the actual data through white box attacks. Now once he has the feature vectors, which is seen in SVM or KNN, he can reconstruct the original data set, and once he has the access to the original data sets, he knows that what is the data, what is actually the all the feature vectors of that person. So we will go into see that what is the thing what we are lacking to build our models that is causing this kind of attacks. This is without even information on the data, and with information once they have extracted the feature vector. So this thing we should know what is black box, white box, model inversion and reconstruction attacks. And then we have the inference attacks. Inference attacks is nothing but they have the class, the actual data and the target model which we build, means the data scientists will, and with the class label and the target model, they will build an attack model. How do they build an attack model? They have a class label and the prediction, the target from the target model, we will give a prediction to the users. So the attacker is like any other normal user. He will come use this prediction and the class label, the label what is that the data is getting predicted for a classification. Think of in terms of that, and then he will train a separate attack model, and this attack model will be, then he will put this attack model, attack it and try to get data, the actual data set, try to recover which data corresponds to which class, what it could have, more information on the ML data set, the actual raw data set. So, and here you see that what is standalone membership inference attacks. So he has two models. One, just don't go into the details of the picture, just listen. There's two models. One is which is deployed on cloud. One is with data D, another is with data plus some change in the data sets. So there are two models, F and F delta. One is trained with D, and see on the right hand side the figure, and another with F delta. So now small things have changed. Now what he will do, he will try to attack the model with trained with D data set and try to attack another model with D delta data set, which is the model F delta. Now once he knows the outcome from this model and this one, he will try to infer what is there in the actual data set, because of a small change, he will know that for this difference in data, this is the model, for this difference in data, this is the F delta model, and how they are behaving. From that delta model, he will try to infer the actual data record that is present in the data set. And then federated learning. So why I'm giving this a little bit overview, because we will be covering how this TensorFlow encrypted packages can be used in kind of single learning or federated learning. So that's a brief introduction. We should know that this is happening. So what is happening in federated learning? Lot of users are sending their data, input data, to a central server, which is learning the data set and using the gradients and converging the model, right? Building the model. Now, what is happening? So what is the objective of any training system? It is to converge it towards the direction of the models by descending the direction of, minimize the loss by in the descending direction of the model's gradient. Now the attacker, what he will try to do, he will try to change the gradient in the opposite direction, in the ascending direction. So once he's trying to change and the model doesn't converge for that data point, he will know that these are the points that is causing problem to the model. The model is not converging. So that are the data points that is causing problem, and that are the data points that are there in the training data set. His objective is to know what are the points that are there in the training data set. So instead of because the model converges towards always the descending direction of the gradient, his objective will be to make it opposite to the ascending direction. And then where it is not converging, the members which are present in the data set, they can't change the gradient. They will always be going in the opposite direction. But non-members, their gradient won't change because they're not there in the data set. How their gradient will change? So this kind of federated attack, mostly you will see this kind of attacks happening in IoT devices. Lot of devices are there, and there is a central server. They send their data to a server, and the server trains the model gradients, individual model gradients, and then aggregates the model gradients. So we'll see that how does it happen. And then we have to be very careful, as we've talked about, against this privacy laws, because each of the continents, you will see EU has a federal law, privacy law. US has a federal privacy law. EU has some privacy regulation laws. India, China. I'm sure in Southeast Asian countries there are separate laws for the individual countries, and they have imported, and they're going to impose heavy penalty for those who are violating those, and imposing fines on the companies. So we have to be careful in terms of integrity, confidentiality, authentication, authorization, non-repudiation, and as well as availability. I'm putting one model in terms of adding security and privacy doesn't mean that the model won't be available 24/7. Even if I'm updating any single thing in the model during times of like low usage, like at the night, the model should be available 24/7. So, and also there are intercontinental laws people have come up with. So US and EU and US and Swiss, they have this privacy shield framework. They have different framework to talk about how they're going to share their private information about the citizens between two continents or two countries. And violations we have talked about is very serious. We can, even if we are not able to pay fines, we will end up in jail. So what we are going to do with the global data and privacy laws, let's look at now, go into machine learning, how we are going to handle this. So let's build a resilient system and low impact secured system than giving a lot of fines to the government or whichever country we are violating the laws. Let's see. Now let's look at life cycle. So we get the data. So data we can get from third-party crowdsourced devices or third-party cloud providers or IoT devices, anything. Now, once we get the data, we have to anonymize the data. So that's the first step towards privacy machine learning. Data collection, we aggregate the data and apply perturbation techniques. What are perturbation techniques? Is a kind of techniques that we are used to add noise to the data. And once we do that, with the noise, and remember one thing, it's not needed that we add perturbation just before training. We can add, I'll cover that. We can add perturbation before training, during the training process, as well as after the training process. So there are different ways of doing that. We'll cover that, the Bolton model, how they do at the end of the training. So when we add noise to the system, we are actually storing the anonymized data in this. That is also we are conforming to GDPR related laws. And when we are training with perturbation, the data gets anonymized when we train the data. So it's a kind of a random noise we add. We can add Laplacian, Gaussian noise, and once we do that, we try to train the model, and we train the model, the aggregated data, and this happens continuously, like training and correction. So you have predicted something, and sometime later in the week or in a month, you got to know that was the actual result. So you adjust the threshold between your predicted and the actual outcome, and you try to learn that, and this continuously happens. So your privacy preserving feedback control loop should also continuously happen. So it is like a closed system. Nothing is going out. So you are learning that you have made a mistake, and you are incorporating that to the training data while you collect the data, that is your mistake. And then when you want to tweak excess, do excess tweaking of hyperparameters, or you are want to do excess of while aggregating the data, you want to add special type of noise, you know that this has changed. So you're doing on the modified data set, and you are doing the forecasting. And how do we classify the different privacy preserving machine learning mechanisms? One is the kind of training, and one is kind of inference. Because one is when you are training the data set, you have to anonymize, and while you are inferring, the predicting it, you have a choice that you want to add additional noise or may not. Now one is parameter based transmission. During transmission, you encrypt the data. One mechanism we'll do with TF encrypted is we encrypt the data just during transmission to the central server. And data transmission, that also you have mechanisms of secret sharing, KPI mechanisms, like three-party data exchange, and one will provide you the encryption key, and see a kind of central authority signature. You can sign your data. Then we have in the inferencing technique, cryptonames, offnet. Offnet is is used in IoT kind of thing. How do you obfuscate that data? And multi-party communication. So here, multi-party communication, if you see that I earn $50 salary, so I have to exchange the data with two of my friends during training. Okay, so I earn $50. I won't say to anybody. I will my $50 will be broken up in terms of minus 30 plus 40 plus 30. So that aggregated amount is 50. So that will be shared. The minus 30 plus 40 or plus X will be shared within the communicating parties with whom I am agreed to train the data. So the information about each user gets hidden. And then within parameter, we have model personalization, which is very important, because you think of recommended systems. There, personalization has to be done, because I cannot add noise just like that to every system. We want to have separate categories or segments of users. So there, maybe we may prefer to define our noise function. Then we have distributed machine learning. And then data transmission web, we have anonymization, which I talk about. Cryptography means data obfuscation. No, this may not be cryptographic, some simple obfuscation, or you define your function. Or data synthesis means like you're combining data from multiple sources and anonymizing them, like one with the offnet or multi-party communication. Similar kind of data synthesis which you apply during training. Means during the training procedure, it's not during inference, it's during training. When you have data from different sources, you have separate obfuscation for different individual parties, and you know how to interpret them. And this, how the levels of information identifiable, you can identify the different levels of information which can get leaked. It can be direct identifier as well as indirect identifier. Direct identifier, we can say the name, address, social security. Indirect are all other details of mine, say birth code, license, bank record, credit card, sensors. So all these are indirect, and we have to preserve everything. So let's get into some hands-on also, and we will see how we are doing this perturbation. So as I told you that we have perturbation at the input, or in the while training the models, or at the output. So one is like we do add Gaussian noise to the covariance matrix, like the PCA. So you know that dimensionality reduction, I'm sure you know that dimensionality reduction problem PCM is solving it. So once we have reduced to number of dimensions, like from 10 features you have reduced to 2, you add the noise to the covariance matrix. So similarly, another mechanism is in each iteration of the covariance matrix, you add the noise in a differential private manner. We'll cover differential privacy. So you'll see this is a little same thing, but in a little bit variation. So each, instead of doing at the single at one step, you're doing at multiple every iteration of the PCA, a PCA matrix when you're computing the PCA. Then adding noise at the output. So it's a Bolton model that we will discuss, that uses TensorFlow differential privacy, and that adds noise at the output. Means before, after training the models, before giving it to the users, it adds noise. And then objective function. So you want to, you have optimization problems, empirical risk minimization. You add noise to the objective function, and then once you add noise, then that objective functions what you have to minimize also gets changed, and then the whole data, you can say, you can anonymize the data. So simple, whatever I discussed, a simple way that whether you add it at the input before training or you add the noise at the output. So let's do some what do you say, the anonymization technique. Let's have a look how we will do in terms of code. So this is one K anonymity problem. Okay, so what we do here, K anonymity means, if you see, so I get some data. I have so much like age, working class, education, some sensitive information, sex, race, capital gain, capital loss. So these are for individual that should not get leaked to the outside world. So K anonymization means I will create partitions. So this is the function that does the partitioning. So links are all shared. You will get access to this. These are all open source. So I have to partition my data set in such a way that I don't disclose the actual education. Sorry, so actual my actual age or my actual capital loss or capital gain. That would be partition in terms of the classes. So now what happens, I partition the data sets, I apply a algorithm to partition it into different partitions that hides my actual information. Now when you see the diagram, you will know. See here in this diagram, what we try to do, all the partitions are having definite boundaries. So you see here, I hope you are able to see my screen. If not, just let me know. Okay, so here you see the age and education has one income boundary. So I'm not disclosing the income. It is to 20K or 30K. So it is within a boundary. So it is like adding a boundary to the K anonymization, to the actual data set. But there may be problem, you see, why we have evolved over K anonymization. So if you see, there may be members who have the actual value, means like everybody is around 40,000, 40K to 41K. So every partition is similar. If all the values in the partition are similar, so adversary can somehow get information about one partition, and then he will know everybody's data. So even if it is like it's not uniformly distributed, because in case if most of the members are centered around one value, then there will be very close one partition or two partitions, and then the adversary will get to know that it's all similar, it's all uniform. Will get to know that what is around the mean income of the person's income is individual. Now we have to diversify it, like we have to spread it across the different partitions in terms of different boundaries. So how do we do that? We do with I diversity. So I diversity, we do that so that the partitions are diverse. So at least one data in each partition should be different. So even if this all the data, except consider of this partition, if all the data is similar, then everybody's information is linked. So what they are trying to do is one participant should have a different value of income. So that's how we have to define our partitions. And then you do that. If you want me to run, I can run it. So here because it will take time, so I have so many things to cover, so I try to explain you. So once I run it, you will see that this diversify function, we have partitioned the data set. And once you see, once again, I have to run it from the beginning. Let's run this iDiversity. Yeah. So what will happen? So here you see one data point or two data points are different. So the objective will be to not to have a uniform partitions, but at least how many? At least one. So it may be more than one. It's one. It may be more than one values which are different. So this is the graph we got. Then we have to. Then also the problem is, obviously the adversary who comes one or two values which are different, he can try to get the values of the other two. So now what we have to do, we have to incorporate that the distribution of each partition should be like that it is resembles the entire data set. So each partition should be so much such created that the overall distribution of the data set should resemble each partition. And how we do that? So that we do with T closeness. So here you see this is iDiversity. There are two different partitions, greater than, less than, equal to 50K. So there are different members to these two partitions. Now T closeness, if you see, there are multiple the distribution, entire distribution should resemble, each of the partitions should resemble the entire. So if you think of this entire distribution, you see the distribution is like here is cut, here is cut, here is cut, here is cut. So the individual partition should resemble think of this partition or this partition or this partition. So here it is cut, here there is no data points, there's no data points. So that should resemble the overall data structure. So how do we use that, determine that it has been done? So there's an algorithm, I think you must have heard, Kubert divergence, KL divergence factor. So that measures the difference in the distributions between the partitions and the overall data set. And that is an algorithm. You don't have to do anything. You have to just run it with the algorithm. But we should know what is underlying happening. So that's how we measure T closeness. And that's, you see, T closeness is done. So there's different partitions, and there are different, not one. There is more number of members here. And the age and education, it's very close, like age and education is this. So every more granular partitions are available for this one, T closeness. So let's go back to the slide. So this is one of this input perturbation, output perturbation. Then the anonymization I have shown you with T closeness, iDiversity, K anonymity. Then we see that when you train the algorithms, what are the factors you should consider? So you should consider that you restrict the prediction vector to top K classes. So we should not have, like, we are predicted 100 classes. So instead we should compartmentalize. And the same concept is coming here also when you do K anonymization or iDiversity. So compartmentalization is very important, and that's give you more, not to from fine grain to coarse, means like it's from very fine granularities you give a generic value, and coarsen the precision of the prediction vector. Like you round it up. Suppose your prediction logistic regression is giving you prediction 0.005 or the probability is 0.9999 something. So you will give 0.9 or 0.677. So you will round it up and give 6. Increase the entropy of the prediction vector. We know that entropy increases randomness of the system. Okay, so that is the objective. So we have to increase the entropy of the data set of the data set of the entropy. So more disordered, most disordered adds more randomness to the data set, which would be difficult for the predictor to predict it, the adversary to predict it. And then add regularization. I'm sure you have heard of L1 and L2 regularization. So we have to add lasso, reach, or elastic net, combine L1, L2, and ensure that our model does not overfit. You remember that overfitting is the main cause of any attacks in machine learning. and the cloud providers where we deploy our solutions like GCP or say AWS or Azure, they don't provide us a mechanism to say that your solution is fit and it cannot get attacked by any adversary. It is our duty to see that we train attack models, or we have fulfilled regularization metrics, and we have tested that it is not an overfitting solution that can be safely reside in the cloud and can be consumed by end users. So this is one very important thing, regularization. And like K anonymization, I've tried to provide all the links in the GitHub, like which are available, full box, adversarial robustness toolbox. So these are the mechanisms which you, if you are just building your library, so ensure that you have used any of these techniques or K anonymizer to anonymize the data. But if you're going for solutions like directly from TensorFlow, you can just take their library and they underneath handle all those things. So we'll come into that. Now let's see federated learning with TF encrypted. So TF encrypted is a package by TensorFlow, Google, and they have done a lot of things with that. And even the PyTorch framework which has come up, so they are also including federated learning with privacy. So let's look into that. So public, let's understand that what is the difference when we do this, talk about this privacy between normal public training and private training. How does it differ? So normal training, you will just import TensorFlow package, provide the weights, this is the model weights, input, and you train it. Like you use a ReLU function, activation function, you apply your bias and multiply the weight vector with the input X, right? And for a hidden layer, you add a hidden layer and add the bias, right? So this is layer 0, layer 1, layer lot, and your output layer. And you predict it, you run it and predict it. Have a careful look at it. And then what is the difference when we do private training? So here we have to, of course, import the TensorFlow encrypted package. And TensorFlow encrypted, when we talk about, so you think of this as a federated learning, so there will be one model owner who is going to just train the models based on the data it has received from other participants. So, and it will get the weights, it will get the weights from the different model participants, rather say, and then it will define this prediction client, get the prediction input as private tensor, and then it will get the private input and train it. Now how does it do that? It's the same thing here also. The compute prediction is only the data is private on the from the individual participants, and it defines, process the result, and gives this same output to a channel. Like there will be one channel where it will publish the results, and that can be listened by the clients, and that can get the results from there. And you see here is like a session, you will run the same thing as the public training. We will do a one, I'll explain this, and then we'll go to the code. So there is a TF encrypted. I am using this PySip, that's a wrapper against the TF encrypted package. So that there can be one data owner, or there can be multiple data owners. So the problem we are going to solve is like we have two data owners, and the model owners, they train. See, think of federated learning. You can train a partial of your model, and you can send it to a centralized server that will act upon it. Means that will do a more combine the models from different owners, and that will do a more centralized training. So that is the main data owner, and it is gets the data from maybe 1 to whatever you want to configure based on your use case. And it has to compute the gradients as privately, as private input. So it gets the data from the data. See, it is zipped because they have two model owners. It will get the model owner name, it will compute the gradients, and it aggregates the gradients. So main function is compute mean gradient, because there are two participating owners. Cannot take one individual's gradient. I take an aggregated gradient, and we reveal only the gradient aggregated against the model owner. Once I define the output, and I publish it again to a channel, and that can take the and these owners can take the the aggregated computed value and distribute it to the end users, the devices. So let's see how it works. And this is the same thing as normal session running in TensorFlow. So let's see this one, this code. So this is the library PySwift. You can use it and download and see, because I use this PyTorch because it was just having the Colab's setups, Colab Jupyter notebooks, and it has the federated data set also. So it you think they took the Boston data set, simple Boston data set, and then we have the like base data set. On that it federated data set. Federated data set in terms of like it partitions the data set saying that there are so many workers. So these are like the participating workers or the participating clients for federated learning. Now we have the loader. We load the federated data set and then we compute we aggregate the model gradients. So we run it, the model, and for how do we get it? You see that we have to iterate over the train loader, and the participants, this each of these participants has to commit here. And how do we do that? That we will see that how does we have here Alice feature for each of the participants. We take the data, we build the optimizers are for each of the participants, and we train the data for each of the participants. For the each of the APOs we send the data also. See, this is the model sent. You have to send the data to the each of the participant. And how we get from the channel, I'm talking about the channel, they publish the data and they get that data. This is just a basic training from multiple sources. Now that we will see. Before that, we also look at the I'm showing the breakups because it will be easier to understand. If you don't understand, we'll take up the questions later. So then we will see the how the channel publishing happen. Again, the nodes has to be separate. So say nodes means the participants in the federated learning. So one will be the we talked about the CA, like one will be the third party provider which is providing the encryption keys. That is James. James is going to provide the encryption keys, and Bob and Alice are participating for the encryption. So once they have the data, train the distributed data set, we append the distributed data set for each of the which are from each of the computing values from participating nodes. We have the computing nodes, and for each of the compute nodes we get the data and append it. Okay. Once we append the data, we have the train function, and that also we have to do for each of the participants. We have to aggregate the gradients also, and then we have to send it to each of the workers, and then we test it, right? And we have the training and the testing epochs and the performance. Then how do we do the aggregation of the encryption, encrypted value, adding the encrypted aggregation? So what we do, we have the compute nodes. We send the batch updates. So update is over the two models with two models, two participants are there with each of them has their own optimizers, Alice optimizer, Bob optimizer. So remember in the slide we talked about that the gradient aggregator has to aggregate the gradients from the participants. So the model aggregator, this is the parameters for each Bob and Alice, and this is the optimizer that is aggregated for Bob and Alice. So once this is aggregated, the model and data set, the parameters, and this one will iterate over the individual compute nodes. Again, that means the Bob and Alice is there as participating candidates for my federated learning. For each of these candidates, I take this data set, parameter, and optimizer, and I try to build a model. Okay. And then once we train, we encryption is with underneath this is using TF encrypted. And why do we do this fixed precision? Because fixed precision is the floating point, in multi-party communication. When we share a secret, or we see this James is sharing the secret key to encrypt it, that does not work with floating point numbers. So we have to use a fixed precision, and that will convert it to integers. So that is the reason for using fixed precision params. And once done, it will clean up. So this is the entire thing with, and this fixed precision underneath they uses a separate gradient. It's not the stochastic gradient, that is they have auto param gradient that will take care of the gradient convergence, that how the gradient converges towards the to have the model fully trained. So this is the difference, is another difference that we will see compared to normal public training. Okay, and new parameter, when they try to always average based on Bob and Alice parameter. Always aggregating means averaging out from multiple participants. And you can run it out step by step, convert it to a Py file, run it out step by step, and see how it is working. And so here also same thing. This is just the entire code what we have discussed, put it in one place. How do we train accuracy? This one, get precision, average, and no gradient. It is how it is applying. But when you do this precision, no, it underneath takes one autograd gradient. You can Google out and see autograd gradient, and then underneath it applies that fixed precision. On that fixed precision optimizers on the fixed precision, it will apply that gradient. And this is the loss and test. So, and also you can look at this one. This I wanted to show you. This is how the neural network is defined. Same thing. This one is more federated learning with secure and aggregation. This is on encrypted data set, neural network. This is the just that they have defined the neural network. The difference is that, and there's the input data set. Then encrypt the model and the data. Here the actual encryptions, what we have seen, after getting the data, they are encrypting it or sharing a secret and encrypting the parameters. But here the model and data both are encrypted. So the data which is guessed from the participants and the model it is building are all encrypted. And how do they are doing it? They're sharing it with this fixed precision. This is the main thing that you have to look at it. What is fixed precision doing? If you're interested, you have to Google and see what inside, debug inside this, put it in a PyCharm. I didn't put the code in the PyCharm. So you put the code into PyCharm and debug step by step and see what is happening here. Sorry, there's so many things open. So fixed precision, and see that this is the auto tensor, and you will see they have the PyTorch autograd. So PyTorch autograd will and it's a kind of a gradient descent. So underneath it will be using that and train your model. Impact of fixed precision, you'll see whatever I had discussed. It requires a grad. You have to set it true, and it's underneath doing it, and that's build your encrypted model with encrypted data set. And now we will see how we are doing it with before I come to hybrid learning. The hybrid learning is combination of differential privacy. This I'll cover after doing differential privacy, like how the sharing of the data is happening. We have seen that we have built the data set, we have or on the encrypted data set we have trained the model, encrypted the model. Without encrypting the model, we have trained on encrypted parameters. Now let's see how the sharing of the model happens. Let's secure sharing. So let's run this. This is the server and this is the client. So one will train the data set. This model, this piece of code is going to train the data set, and this is the client which is going to consume it. Then how, let's see how it is happening. This is a normal regular imports. Okay, now just a model like a CNN is done. Like it's because it has a data set which is going to predict 0 or 1. Number of classes is 10, and this is the MNIST data set. You know that is 20. It costs 28. When you flatten it, the height costs width. And we take the data sets and loss the workers. The workers are nothing but you are starting a cluster, and you have to ensure if you take that GitHub code, it will be false, but you have to change it to true, because if you change it to false, then it will understand, this piece of code will understand that you have already some mechanism of launching the servers. Okay, so unless you're doing auto manage your own manual management of servers, you have to change this to true. Then you run it, TFE worker. So you have 3 worker nodes, 3 participating nodes, and which forms the cluster. Your cluster has been started, and you're sharing your model through the cluster. So that's the channel where you're sharing your model. Okay, and you serve the model once you share, and you have to serve it. Now once you serve it, the client has to query it, right? Otherwise how it will work? So the client has to get the data from this. So client, let's see how the client will get the data. So client has the training data, and the test data, it will query to the server, and the server will Client knows to whom to talk. You have to connect to the model. This is the channel which I'm talking about, that they are talking to each other with by means of a server client configuration. That's the channel he's subscribing. That through this he will try to get the model, and he will try to query the model, and he's got the results. So here you see the server code is also run. Okay, server encrypted results are sent to client, right? And then you clean up, stop the cluster. Always do cleanup operations so that you are not leaking any memory on your system. Fine. So we'll take the questions. Just note it down. If you have any doubt or anything, we'll answer it at the end. So you have to do it on your try it out your own self, and then build some assignments you can do combining the hybrid model. We'll talk about that. Let's go back to the slides. Yeah, so what are the challenges? So challenges, you see that many of the devices or the IoT devices, mobile, has very low power. So if we think of that, the data will be, you have to send the data to the centralized server again and again. The parameters you have to send, the gradients you have to send, and the server is going to aggregate. So that's a challenge because they are low power devices. Sometimes battery will run out, and they will be running whole overhead. So many parameters, huge data sets, so many parameters. So, and then so many processes of model upload, model download, your individual personalized model upload, then he will aggregate the model, download. There's a lot of power hunger. There will be power shortage for these devices. And then data transmission also, everything you have to do encryption. Again, you have to apply encryption at the device side, transmission. There's a lot of overhead. Otherwise, your model will be susceptible to attacks. Now, differential privacy has come to overcome the challenges. Differential privacy is a mechanism that helps you to do at the application level. So while that anonymizes your data at the application level and trains it. So once you have something like you can have a kind of like a distributed hybrid system where you can eventually want to send some part of your data to the cloud, that centralized server, and the centralized server will train based on differential private models. So how does it happen? So data set, it's kind of an abstraction such that the mean, variance, and median computation are, you have that, you know, what's the data representation or the distribution of this current data set, and you're going to abstract it in such a manner that if you change any single output in the input, in the number of the single input data point or data record, add it or remove it, that's not going to impact your predicted outcome. So the adversary, when he sees that x plus delta, remember we have talked about the delta data set, right? Delta plus delta data set coming in with the plus delta model, and without the normal D data set, the F model. So when you change a single data point, there should not be any change in the predicted outcome. So he has no way of knowing that this data point has changed, so the model is changing its behavior. No change in model behavior, same probability of outcome, so no information leakage. And it's suitable for large data sets and distributed systems. And we'll see how we can use this differential privacy to build distributed systems. So that gives you protection again, differentiating linkage attacks as well as reconstruction attacks. As we have discussed, you have D data set and D dash data set. So what is the difference between D and D dash? So this is the only image, this image is changing, and rest all are same. Check this. So we have two different inputs, and this is D probability distribution on D data set, probability distribution on D dash, and they are goes in terms of statistical distance, and by a single individual they are different. And how do we estimate that what is the privacy of my model? So that's given by privacy budget, and it is represented by in terms of number of queries that it internally the library is getting to estimate the budget. So let's see how it is distributed. The privacy budget is epsilon, represented by probability of a data set D dash D1 belongs to a normal distribution, divided by this the other data set. Probability of this data set should be less than equal to e to the power epsilon. So e to the power epsilon should be like, we are thinking of epsilon should be as small as possible. to have a build a highly private model. So if it is like 2.2, 0.3, 0.5, it's very private model, right? And you're thinking of e to the power of that, so exponential of small number. So you can imagine that how small my privacy budget will try to make it. So that would be the ideal case. Again, we'll talk about there are trade-offs, how do we optimize those trade-offs. Now, how much noise you have added, this is called the norm, the term absolute value of q of d, the noise what you have added, d1 minus d2. And that is like this randomness is similar to like when you when suppose I go in a crowd and ask people to tell me a number 1 or 2, so they won't tell me, because they will think of that I will know the number what they have guessed, 1 or 2. But if I ask them that guess a number between 1 to 100, that adds randomization, so they will guess it. So it won't be that easy for me to guess the actual number. So that's why differential privacy system, that in terms of representative probability of coin tosses, like it's like 0 1. No, it's not that. We have to if you give a larger set which you can able to guess, that's going to be the randomness in the system. So it's a similar thing, that how do we do it in terms of machine learning? Like this is the loss computation on the input data set, and that this is the between the prediction and the loss. So this is we try to minimize the loss. So on input data you add a noise. This is nothing but noise added on the input data, and you have clipping the gradients. So remember, this will talk about tensor for differential privacy applies this, the clipping of the gradients. Why it does that? So if you see, some of the points are contributing a large value to the gradient descent. So if that happens, then what happens? The probability of impacting a single point on the output value will be very large. So this gradient clipping allows any point not to contribute any too much towards the model convergence or towards the model output. So everybody is limited by a maximum value. No point can overpower the other, its impact on the output. That's why we use gradient clipping. And then input data x a label, and you as you try to minimize the data, this is your error matrix. Evaluate the what do you say, the differential value of that loss, because it's back propagation, right? And clipping and adding noise, these two steps, Gaussian noise we have done, we can add Laplacian noise, and then you compute this continues in steps. Every step you do that and compute the final error matrix after the model has converged, and you observe the privacy estimate. What is the privacy you are getting from the after the model has converged? What is the epsilon that you are going to measure? This is the simple step. It goes continuous step by step. It's an iteration, like compute the loss, minimize, compute the loss, minimize. That the TensorFlow differential privacy uses this library called RENYI differential privacy. So what is that? It's what we have defined is that, but it is built on top of it. It has cumulative loss computation, privacy loss computation. So every query the library gets invoked, it computes the loss incrementally, the privacy loss. So it's a cumulative computation of the privacy loss, and the privacy budget. It tries to, of course, the goal is to minimize the privacy budget, and it adds more stronger privacy and handling over a lot of heterogeneous data sets. So that's the usual definition for RENYI differential privacy. There is a paper for this RENYI differential privacy. I've tried to put it into the links so you can see. This is a randomized mechanisms that D maps to a real number is said to be differentially private of order alpha when alpha and epsilon, that's the privacy estimate, if for any two data sets D and D dash, it satisfies this criteria. Okay, it's just a differential privacy, and on top of it, they have tried to add some more stricter mechanisms for having a better privacy budget, and that's what gets included in Tensor for differential privacy. And remember that we cannot just go around making the solution very private, because there is a trade-off between the maximum accuracy versus privacy. So we have to arrive at an acceptable trade-off between utility and privacy. So that's the ideal situation, that your utility is also high and privacy is also high. But that doesn't happen. We have to make a trade-off. And then this is the hybrid model which I was talking about. So what happens with the hybrid model? So this is the model owner. Okay, so model owner sends the encrypted model base to server 1 and server 2. So here you can use whatever GCP component you want to do, like that you can use your like the data prop to train the model, or you can use GCP's data lab to train your models, where you have the TensorFlow workbook, the GCP workbook notebook. Once you train the models, you send the model bits to the server, and this model server also gets the data from different devices. Now, if you want to aggregate the models, then better to have differential privacy-based algorithms. So each of them have differential private algorithms. They send it to that. You create an ensemble model from this all the heterogeneous devices, and then once you have it, you send the model back to the devices. So this kind of hybrid model. We have talked about only TensorFlow privacy, where we see federated learning. You're sending the data either private or sending the model vice versa model private. Now you're sending differential privacy-based algorithms to them. And then because at this level, your privacy is incorporated in the individual models you send. Now the server's task is to aggregate the models what we have seen, and then gives the result back to the individual devices. It's a simple thing, like the TensorFlow differential privacy. It is built on PATE. So I put some papers links you can read about. They have advanced this PATE in terms of like its scalability, the way the gradients are aggregated, the gradient vector, and how they are doing it without having a discriminator and a generator, and how they are like the data from the generator to the discriminator is just published. It's not that we have to always integrate at the generator and the distributor, but they have made a way of publication the data from the generator to the discriminator in such a way that privacy is incorporated, and the end users who are communicating to get the model output is not communicating directly with the data generator. They are just taking they are getting an output from an intermediate model. So they have advanced over several layers. You can see that. So you see the data sets getting and you can pass it. This is the gradient, the DP aggregator, the differential private aggregator, which aggregates the gradients from different devices. A case of federated learning, imagine that. So noise, so you can add external noise, what kind of noise you want to add, and then you have train an unlabeled public data. And the idea of this, when you're training on an ensemble model, that you maintain a low privacy budget that will increase the privacy of the model, and high teacher consensus. These are called teachers, individual models. And this teacher consensus is high means like all of the models individually are agreeing that this particular data point belongs to class 6 or class 7. And low teacher consensus, they are disagreeing among themselves. So one is saying 6, 7, one is telling 8. So what happens is that when the output, when a client request comes, the student is going to reply after learning it from the teachers. So when the student is going to reply from an aggregated model, it can't find an answer because all of them have disagreed. There is not a high probability of stating that this is the output class. So the objective is that the high teacher consensus, that all of them are agreeing, and that gives a high probability that this model belongs to this class, that can be easily answered by a student. So that is the compartmentalization. Like the external request which comes, that is directly not talking to the teachers who has the actual access to the data set. So the answer is only given by the clients, like who is the it sits here, say suppose here. So he is going to query the teacher if he doesn't know the answer, because it is also learning in terms of time. If it does not know, it is going to ask the teacher and is going to reply. So there is no access of the client communicating to the teacher because it has access to the actual data. So more privacy. So how do we deploy those solutions and take it onto the cloud? So there are two concepts. One is the one is the local differential privacy and is the global differential privacy. So local is like we assume that the aggregator who is going to take data from different sources is very untrusted. We cannot trust them. So individual owners add noise and send it to the curator who is going to condense all the data sets. While as global, and this is mostly used in industry, if you see differential private solution, the one is used by Uber, the Chorus network. So I didn't cover that because I thought that it will be too much. So the Chorus network, you can Google in Google out that used by Uber is using this, the local differential privacy solution. Most of the solutions are local, and the global differential privacy, like you get the data and you know that the data who is aggregating the data is can be trusted. So no need to add noise. So you take it from data sources and give it to the curator. Curator will add noise and it will distribute it to the end users. And here you get the part of data. So once you send it to the curator, curator adds noise, analyze, and send it to the answers to the individual participants. So let's see in a production how you deploy with an edge computing with say IoT. How do you define that? So you have data compression, like because IoT is a lot of power hungry devices. They can't send huge volumes of data just like that. So there will be volume, velocity, variety, all these are differing, right? So they must be sending data in some form, compressed zip format. Once you get that zip data, aggregate that, and we add obfuscation techniques. We have talked about obfuscation techniques. We integrate data at the edge servers, so the servers which are deployed close to the IoT devices. Let's use edge computing here. And then we have the Google TPUs, which is going to do that, and it is decentralized mechanisms, lightweight. We can have individual edge servers and stream the data. It is lightweight, and we have to have composability so that we can integrate aggregate and integrate the data, and adding perturbation. Now what happens after we are doing aggregating the data on the edge? We have Spark. Equivalent is the data prop. You use the data prop to compute the algorithms, like what algorithm you are going to use on the raw data. So once you do that, and you have separate, you can create separate individual algorithms or ensembling the what we have talked about. Once you have done that, and then you send it the composite algorithms to the differential private algorithms to the end users. And this is one, like let's go into details what are the components that we can use in Google Cloud. So cloud, these sensors are there. So this is coming, it's not same as the previous one. So how do you ingest them? So you have to have Google GCP pops up. So you have to subscribe to a channel which is going to get the data, and this we should have monitoring that what is getting ingested and that logging mechanisms. Now before the doing into the IoT cloud, we should have a gateway. So the devices data we cannot directly ingest to the Google Cloud. We should have a mechanism of cloud IoT that is going to give us data to the the cloud infrastructure. And how that's get communicated from the devices? You take a gateway, the device data that should pass through gateway, that the MQTT bridge, and that gets passed to the cloud IoT, and that is giving us the data to the cloud system, main cloud ecosystem. And then once you have ingested that data, you store it in the cloud storage data store, a big table. This either you choose SQL types of means of storage or no SQL, and then you here the application, the presentation, that is the compute engine, container engine, or the compute engine. Then here we may want to do some advanced processing. Like if we are building our own algorithm, we may not use notebooks. We can just pass it to the another GCP compute engine, and we build our own notebooks. Sorry, our own ML models. So notebook is more of a, if you want to use data lab or data say, I'll cover that also, data lab or the other one, they have the data prep. Okay, so that preliminary discovery, data discovery or research purpose you can use. But once you want to build like a live system or that runs 24/7 and the auto correction or auto error correction mechanisms are on, you may want to put it into exactly a container or compute engine. Like it will auto scale. So if your volume of data is used, you have already done your research on data lab or data preparation tools on Google. So but you know that which features works well. how. But if you want to run it at a 24/7 pipeline, better you go for compute engine or container engine, where if container engine you will have auto scaling the pods that can scale your that can get scaled based on your incoming data. So there you can apply the feature transformation, write a Python script, deploy it in compute engine or container engine. Everything will be taken care of. Okay, and then the cloud data flow, it comes cloud data flow. You can store it, you can process it with the cloud data flow, and because if the cloud data flow will be taking the data from the ingestion engine that the pops up, and then you have the normal exploratory analysis you can do, or you can train after you train your algorithms, you can do an analytics on that. So if you have stored the data for cloud storage for a long time, and you can just directly pull out the data and do an analytics. You can also plug in within your analytics tool the data prep or the data lab. So for research or data discovery purpose, that how the plots, what are the features, how they need to be normalized, standardized. But if you have to have a 24/7 pipeline running in batch updates, and you have to tweak it, you have to understand the error, how they are changing it, and give output the clients are consuming here. There's an API over here, and the clients are consuming it, then better go for a container engine or compute engine. Let's look at TensorFlow mechanism with TensorFlow privacy. So there is a, like we have talked about that Gaussian noise, Laplacian noise. So this a bell curve of a Gaussian distribution. So, and also we have talked about the clipping of the gradients, like how we do the clipping, that every gradient, all the each of the points gradient should be limited by a maximum value, so that the gradient descent optimizer there has and on top of it they have built another one, so Adam gradient descent optimizer, or you can call Gaussian gradient descent optimizer. So that is built on top of the normal gradient SGD we use, our Adam optimizer we use. And the privacy ledger keeps account of the privacy budget, and we should take care of privacy versus utility. And joint clipping of the gradients, how it clips the gradients. So group of privacy vectors are there. What are the parameters that you want to have it private? Like everything should be anonymized. And it gives you more flexibility on mini batches, so and micro batches. So you can choose to be, see, in normal training we do a batch size of say 256 we do. So here they give more granular control. You can control in terms of not only in mini batches but also micro batches. I'll show you the code. Let's go into this and a hybrid model code and how we can do that. And from logis equal to true when softmax layer is applied. So you have to see whether you are applying a softmax, whether you need to apply a softmax layer or not, and what are the impacts on the model privacy. So just don't plainly apply a softmax layer. So even if you're doing from logis equal to true, apply the softmax layer. So we have three different modules. That is, one is training it, one is configuring the privacy, and one is the accounting. So and this is I think I will cover the bolt-on after this demo. Let's go through the code. So we have the bolt-on differential privacy and how we do it. So a few slides are there. We'll cover it after going through the demo. So I have a blog. I have shown how the code in differential privacy works. So I've read. So there's one issue. I have written to TensorFlow, but I have not received a response from there. So this code I checked it during January, February, I think. So they have, and it was working fine. I have the working that how it works, the losses, everything, the outputs it gives. But the problem is they have released a new version, and for that there is a one issue is coming, that the shape is, they're telling the shape vector is not proper. The input vector is not proper. So they have not responded. The 113 in TensorFlow privacy, you can see I have raised one issue, 113 with Google. So they need to respond. So, but this was working in the previous version. So let's see how you add it. So this is normal. Say I've taken some consumer complaints from the consumer. It's a multi text classification data set. Okay, then I replace this. What is the problem? it's simple from Kaggle. If you think of that, what are the student loan? It can be categorized as student loan. If it is a financial services, these are the keywords which gets replaced with this keyword. Drop duplicates, this is a normal taking the tokenizing the test, breaking them to sequence tokens, and then creating the train, test, and validation data set, and using the glove pre-trained embeddings, and having learned from the glove embeddings what are the data present in your system and not. So creating that embedding metrics, and then this is a sequential. This code you must be familiar. That is creating a sequential model, and with dropout and one dimensional convolution network with the LSTM and dense network, and sparse categorical constant entropy because I'm using Adam optimizer, and it is a multi-class problem. So now what we are doing is optimizer is your Adam optimizer if it is a normal use case. You don't want to apply differential privacy. But this flags, you see, if you go to the code in GitHub, you go through that and you see flags. You can set this flag that you want to train it with differential private solution. So you add a separate differential private optimizer. That's the only change in your code. Rest all the code remains the same. Normal text classification, what you do, you can do the exactly the same thing, only change the optimizer. And they have designed the optimizer. There are other DP SGT optimizer. You can check what optimizer you want to run. That handles these parameters. That is the learning rate, the micro batches. The macro batches you can fine tune. Like you can, instead of 128 or 256, you can put a 64, 16. You are handling the gradient clipping in within the term of micro batches, and in the N2 norm, that's how you are going to clip your gradients, and the noise multiplier, that how much noise you are going to apply. And this is same as normal text classification. You can go through Kaggle and see, and then we compute the epsilon. That is the most important, that the epsilon is the privacy in your model. So how do we compute that? Let's compute epsilon. It's there in my GitHub. Okay, I'll show you from here. Yeah. So here also they have used gradient descent Gaussian optimizer. This is a Colab notebook, and fit it. And these are the three things. And then we have to look at compute. This is the privacy computation, privacy estimate. So the Bastel noise multiplier you can specify, and this N is the this N is like your based on your size of the data set. So we specify N. So you had 60,000 training samples, you will specify 60,000. And then this delta is nothing but inverse of your size of the training sample, as 60,000 training points. So this is 60, and this delta, what they compute for the computing of the privacy, they put it inverse of the size of the training session. So they have taken 10 to the power minus 5. 1 divided by 60,000 is 10 to the power minus 5. They have used for the it is used to be less than the inverse size of the training data set. So remember, how do you set the delta? So that is, they have taken 10 to the power minus 5 delta, and this epoch is this one. So that's how it computes the privacy budget. So epsilon value is 1.18. So this one runs because this has no shape problem, because this has it is already a Colab notebook with MNIST dataset. The MNIST can be directly reshaped into 28 into 28, but the other text classification or any classification, we are facing problem. Another guy has also commented on TensorFlow that they have to let us know why it is failing. The reshape problem is we are facing a reshape problem. And you see here the same thing what I told you, the number of micro batches. It's very important. You can fine tune based on what you want to do. And then norm clip. Okay, and then I show you the hybrid model, where you have TF encrypted as well as you have TensorFlow differential privacy. So there are certain differential private libraries, open source, which I have listed here. I'll go through that. So you can pull out these libraries also, because Google's TensorFlow differential privacy libraries is not compliant to TensorFlow 2.0. So that's still evolving. So better if you can just try it out once or twice and avoid. You can use IBM's TensorFlow, the differential privacy also, because and you have to follow up on the issue I have raised also. They are not responding, so that thing we have to do. And then you install PyTorch. You can also use PyTorch DP. There is another library available which you can try it out. This works, but I can't show you it here because I don't have GPU. So that needs to be used on GPU. And then here what we do is we apply a hybrid model where the differential privacy we are doing with IBM's differential private leaf, and we add a Gaussian noise, and we derive the metrics like the privacy accuracy metrics, and then we serve the model with TF encrypted. This is the SIFT library, the PySIFT library which I showed you. So like you're splitting up your data, like in terms of that, as you have like 2 or 3 participants, like the data for Bob and Alice, or target data for Bob and Alice, and then you are applying model aggregation, like the data set aggregation for Bob and Alice. So you have a data set, this is kind of simulation. You're thinking that you are splitting in terms of two participants or 3 participants, you can split it, and then you have to apply that aggregation model aggregation, and request grad equal to which I told of the PyTorch auto grad. So you have to apply that, and then you get the model, and then you again apply the channel distribution. You can send it to Bob and Alice, the set up a server, and that the client can listen to the server, the channel, and then the model can be published. So the intermediate, the application level privacy what we are building is with IBM's differential privacy. You can apply TensorFlow privacy with that if that issue is not there. So this we have talked about, and then let's go back to the slide and see what else is there. Yeah, so bolt-on privacy. Next, we have to talk about bolt-on privacy. So why bolt-on privacy? So it is because more of trust and performance. So TensorFlow privacy, there is one company contributing, and they have built the bolt-on DP. So what is happening is you take data from different sources and different data sets, and try to build an ensemble model. And while you build the ensemble model, you add noise at the output. Remember, we have talked about perturbation at the output. So here in bolt-on DP, that's what exactly we are doing. We are adding noise at the output, and we are getting the aggregated model. And when we do that, you may say that suppose there are hierarchical relationships in the data, so that relationship is preserved when we are applying noise at the output after the training part. So that's the beauty, and that's why it increases the trust and performance. So you can get different kinds of data sets from different sources and integrate them. And so because it is from multiple sources, that all the information is not available from one. Even the adversary can attack the model, but he can't be able to link it the way that is done. The linking part is not available. He won't be able to link it, and it increases the trust and performance of the customers and users. So how Bolton works? Bolton injects noise at the post-model convergence, output perturbation, and the relationships is maintained between the feature vectors and L2, and it adds L2 regularization or L2 sensitivity. And it has limited learning rate and convex loss, and it also preserves maximum utility with privacy. So I've put the research papers. If you want to go into deep into differential privacy, Bolton differential privacy, read about how it is doing, you can read about it. There's less runtime, better convergence, and how does it work internally? It projects the weights to radius of the hypothesis space after each batch. And it is very easy integration for ensemble model prediction. And so how does it add value? It helps to get more customer, as we have talked about, that helps to get win more customer confidence, trust, performance. It also gives an opportunity for customer contracts with partners, because the legal bindings is more easy with Bolton differential privacy, because they know that they can more open up to share their data in this kind of models. So they can data aggregation from multiple things becomes more easy in terms of legal formality. So it's a build models with siloed data. Marketing or legal bindings, it becomes more easy with Bolton. So let's see the code part of it. I put a screenshot. So normal, we have seen that non-DP versus DP versus Bolton. Let's take an entire look at the full situation, what's happening. So private public learning, we have talked about the sequential network we use, sigmoid or whatever activation you want to use, ReLU. And then you have a binary problem, simple thing, L1 into regularization. Now we go into differential private solution. So you can define your gradient descent optimizer, right, and or the Adam optimizer. But once you are going for a differential private solution, you can have your flags defined, like what is the learning rate and to norm, batch size, epochs, micro batches. And then when you do that, you have to add your own, that noisy gradient optimizer. Either you add Adam Gaussian, Adam gradient descent. There are other optimizers also present in this TensorFlow privacy. Have a look at it. What are the optimizers that you can use? And you have to specify that what are the how you want your model to get trained, the noise multiplier, how much noise you want to add, the crimping, the L2 norm. Well, in Boulder is very simple. You just have to add L2 and see the radius constants. We have talked about that they projects the parameters onto a radius space. Okay, and the Bolton model. Just call the Bolton model with normal SGT optimizer. But the loss they specify this is a convex optimization problem. Use strong convex binary cross entropy and with L2C and radius constant, what we have defined, and simple 3 to 4 lines of code. So if you can do the Bolton model, I'll suggest better to go for Bolton model than than TensorFlow privacy, because it's built on top of this TensorFlow privacy. So it's a more advanced version of it. And then what are the design technologies that we should take into consideration while building differential privacy? Like the domain problem, we have to understand the domain problem. What system we are going to make it a private learning. Okay, model privacy in events of different sizes, whether we are going for Bolton model, we have data from different sources, or we are going for a single model. But what are the privacy? What are the parameters? What are the features that are very private to my modeling? So that features we should be knowing that is not getting leaked in any way. Then the budgets, and then the privacy budget, nothing but personal privacy budgets, the deployment mode, how we are going to deploy it, and storage for streaming data. And data is coming from streaming systems, like mostly IoT devices will stream. We have to have a streaming network, like we should have a data pub sub with data flow that is able to consume the data from the streaming system. And that is continuously, remember, of the privacy preserving life cycle, that we have to continuously monitor and train our models. And compression techniques, numerical, categorical variables, everything we should ensure that is getting properly labeled before we are proper encoded, the label encoding or one-hot encoding, before we pass it to the differential private system or whatever privacy we are trying to incorporate in the ML model. Okay, so removal of trusted, we can go for decentralized modeling, where like the multi-party secure communication, everybody communicates and everybody wants to share their model. More from a centralized system, we can move towards trusted party. Removal of trusted party, like centralization, move to distributed models. Then sensitivity, this is just the summarization what we have done. Like the fixed sensitivity we should have, refresh queries for the target population. Then the random sampling, we talk about random point tosses. So if the outcome is 1 or 2, people will think twice that whether I should share my data or not. But if it is random, giving them a large space, they will share their data. And event level privacy, for each event that is getting queried to the model, think of the teacher and the student model. So the student will answer to the teacher, so that every event should be private. So how do we do again with in a distributed system? So you have AutoML. You should use AutoML to capture the hyperparameter, how the model is behaving over time. Then we have, for the data mining, we can use data prep. For the research purpose, let's do data prep, cloud cloud ML, cloud data lab. We can use all those things to have the features created, or we have to standardize, normalize the features. From 2 features, create a single feature. So we can use this cloud ML, cloud data lab, data preparation, modeling, visualization, and then stored in the cloud storage, either in BigQuery system you want to store the data, or store in cloud data labs, in the cloud, like the sorry, are you stored in the SQL non-SQL databases. Once you have stored it, feature engineering and stored it, you have to do the data mining. We are doing it and getting the test data set. But when you went to have an online system like that, which can predict and it can give an output predicted results in terms of an API, let's go back to the previous system which we have discussed. I think you remember that, which we discussed about that. Um, the big data framework, we will have to use this system 24/7 monitoring pipeline. And these are the open source providers which are giving differential private solutions. You can check others as well, other than IBM and Google. So yeah, so I try to put the tools. We can use Harvard University and the other tools in R. If you're comfortable, you can try it out. R. And what are the research? What are the open questions still left in differential privacy? So multi-dimensional time series analysis, anomaly detection, then large volume of data training, noise addition. Like how do we do in large volume of data training in Hadoop ecosystem? Say somebody is not applying like data proc, or that's why I brought the question of data proc. We should have data flow and data proc in place, like it's equivalent of Spark system, so that we have large volume of data training, feature engineering, and end-to-end building the differential private solutions. Because remember that it's not about we add privacy at the model level, we have to add privacy in the big data ecosystem as well, because at the end of the day the company is not giving the model, is giving the entire pipeline, selling the entire pipeline to some client. So, right, so everything should be anonymized, and it's if I only build a differential private model and expose it in terms of an API, my if my big data system is not secure and private and the data is not anonymized, I'm ultimately violating the GDPR laws. So we cannot do that. So everything should be anonymized, starting from the data ingestion to the pipeline where we store the data, SQL databases or NoSQL BigQuery, everything should be anonymized, at least the sensitive attributes. We should have like audits, and we should say that what we are doing to send customers data, like how we are storing it, how we are anonymizing it. We should have some documents, and then these open questions we need to resolve, like noise addition, how much differential private we can guarantee with my present business use case. And it will vary based on volume of data and the business use case. Also, are we, if you're doing for vehicular networks or movement in of data, like recommended systems, location based recommendations, are we adding differential private models? And how do we are we able to guarantee privacy in online data? And how do we combine cryptography? This is the hybrid model which we have talked about. How efficient is that hybrid model, cryptographic techniques in differential privacy? So you're thinking of that, again, the model we have built, think of the application differential private model we have built at each end devices. Now you ultimately have to give it to a server, right? In case of federated learning. So what encryption techniques or cryptographic techniques we are going to apply to again share the model to the server? So these things are evolving. TensorFlow privacy is also evolving. So this is not we have to go a lot. Then algorithm efficiency, the weight compression, the model weight compression, the right selection of alpha delta, multi-party sharing we've talked about, the sensitivity, the trade-off between sensitivity, utility, and advanced methods for DP for virtual clouding. So all these things are still evolving, is under research, and there hopefully we see more light and more advanced libraries coming up. And also have the mapper selection, like that if you're going for map reduce Hadoop ecosystem, not Google Cloud. So how do we select the optimal number of mappers and reducers in kind of differential private models when we are training differential models? The references, questions. Hello.
Hello.
Yeah.
Thank you so much for sharing this and for adjusting in our time in our time zone.
Yeah. No.
Um,
Not any questions. Yeah.
yeah. Let's start with the questions. Here's from Ruben. Have there been real cases reported on security breaches of the type you described?
Pardon, I didn't get you. What are the security?
Security, have there been real cases reported on security breaches?
Yeah, yeah, there have been linking attacks, which I've been telling you from the models. So yeah, people have deployed models, and that this linking attacks and the reconstruction and the model inversion attacks. That are the real cases that machine learning models are susceptible to. So
Okay.
you won't find it a very straightforward way, but if you look into the systems which people have exposed, you go for Netflix and IMDb. There you can see how machine learning models have been attacked.
Okay, got it. Thank you. Next question is from Brian. Are there other metrics that we can check to give us feedback that a model could be susceptible to data privacy attacks?
Yeah, so check the most important thing is the regularization. The model is not overfitting. Okay, the next is the, if you're incorporating TensorFlow privacy or whichever library is there, will be a mechanism of measuring epsilon, and that's again is based on the size of the data set, right? So based on the size of the data set and your volume of like the model you're training, the norms you're applying, the gradient crippling or the optimizer you're applying, you try to see the budget. See, sometimes your budget may be very high, so don't scared that, oh, my budget is high, that means my model is not perfect. No, not like that. You have to see that what volume of data you are training, what are the things you are applying, and how much accuracy you are getting. So it may differ from your use case to use case. So stay alert on all factors. Don't get biased on any single thing.
Okay. I think that's all the question in the YouTube comments. Thank you so much again for sharing your knowledge with us.
Yeah, sure, and just send me the
Yeah,
YouTube link also, if you don't mind.
yeah, sure, sure.
Thank you.
Yep.
Bye.
I think that's all for the Women in Tech webinar. Yeah.
Thank you. Bye.
Thank you. Bye.
Bye.